everybody, and welcome to this Learn Live session, Apply Well-Architected Framework to Your Solution Design. I'm Rupal Modolkar. I'm a Cloud Solution Architect Manager at Microsoft based in Melbourne, Australia, and I'm joined today by my colleague, John.
Hi, Rupal. Nice to be here, and hi, everybody. I'm an engineer in the Fast Track for Azure team, also at Microsoft, based in Auckland, New Zealand. We're also joined today by our colleague Satish, who is another engineer on my team, the Fast Track for Azure team. Satish is in the chat, and he's ready to answer any questions and to provide any information on the topics that we'll discuss today. So if you have any questions about anything, then drop them in the chat, and Satish will get to them.
Today, we have put together some links and notes to accompany today's session. We have included a set of links to some great content on Microsoft Learn and other places. So please check these out later too. In today's session, we are going to talk about non-functional requirements, which we sometimes call NFRs for short. We'll start by introducing what NFRs mean and why you need to think about them early and often as you design and plan your solution for Azure. We'll also introduce the Azure Well-Architected Framework, which helps us to think about these requirements in the context of your own solution. Then we'll talk about some of the most important requirements you need to think about in 5 key areas.
That's right, Rupal. And overall, our goal today is to help you not only understand how to think about NFRs, non-functional requirements, for your own business and your own solution, although we do want to do that, of course, but we really want to help you understand them well enough so that you can start to make informed decisions about the trade-offs that you need to make when those requirements are in conflict, which does happen quite a lot. So we want to enable you to have informed discussions with other stakeholders throughout your organization, because requirements really are a team responsibility. Both business and technical stakeholders need to be involved in gathering and setting requirements. And after today's session, you'll be able to have those kinds of discussions with your colleagues to ensure that your requirements for your system consider both the business context and the technical context. So Rupal, how about we take a step back and think about what requirements actually are?
Sure. John, suppose you're working on an e-commerce system and I ask what your system requirements are. What you think you might say?
Yeah, well, for an e-commerce system, I'm assuming it's for selling physical goods of some kind. So first, I might say that the system needs to let my customers place an order, right? Then those orders need to be sent to my company's fulfillment center for processing, for fulfillment. And then finally, the system probably needs to do things like send the customer an email once the order is shipped, right?
Those are all good, but those requirements are really just the tip of the iceberg. There are all sorts of requirements that are lurking beneath the surface. They might not be so obvious, but they are extremely important to access for the success of the system.
So can you give me some examples of those kinds of hidden requirements?
Sure. So, well, first we have to consider scale. How many orders will be placed through the system? The way we architect and review a system which processes one order a day is very different to a system that has 100 concurrent users placing orders. We also need to understand whether we need to comply with regulatory standards or if there are any special legislative or even contractual provisions that will affect how the system is designed, right, or used. And we need to understand how mission critical the workload is and what is high availability and disaster requirements are. So we separate out these different categories of requirements into functional and non-functional requirements. Most people understand functional requirements well. They're used to talking about the features and the functions of the system, its use cases, user stories, and so forth. And functional requirements describe the behavior of the system and the solution and the information it manages. John, the requirements you mentioned are all very good examples of functional requirements.
Okay, cool. So I can see we also have these larger sets of non-functional requirements, right? And it sounds like they help us to define things like the quality of the solution and to specify things like when the solution should remain effective, what happens in different conditions in different situations, right?
That's right. When we think about non functional requirements, we need to consider things like the capacity of the system to absorb load, the speed and the performance of the system, the security requirements, including compliance and regulatory standards, and availability, reliability, and last but not the least, the cost of running the workload, both in Azure spend as well as operational and ongoing development costs. So, today we want to help empower you to uncover these requirements and to think through their implications. There are several key non functional requirements that we think about in the cloud, and we'll cover what these mean and how you might want to identify them in your own scenarios. Also, a lot of the architecture is about considering trade offs between alternatives and understanding the upsides, downsides, and costs of different options. To do this, you need to have a solid understanding of the business context of the system. We'll talk more about this throughout today's session. You might have heard about the expression leaning left or shifting left. Really, what that means is the sooner you identify and fix an issue, the better. In fact, according to the United States National Institute of Standards and Technology, it's 30 times more costly to fix an issue after you've gone to production than it is during the requirements and the architecture design phase. So, good requirements gathering and good architecture helps us to avoid making costly mistakes by thinking through our solution and how it works early in the design. And non functional requirements make a big difference to how solutions are designed and work. So, it's important that they are considered early and often. And this doesn't mean that you have to get it right all upfront, but it does mean that the sooner you identify key requirements, the more opportunity you'll have to ensure the system meets them. Also, it's normal to focus on functional requirements first and for non functional to come later, but it's important not to leave them too late. If you're using sprints, your architecture and design, for your architecture and design, then something you might consider doing is having both functional architectural sprints and non functional architecture sprints. One of the tools we have available, which will help you with this, is to identify and think through all the non functional requirements, is the Azure Well-Architected Framework, sometimes called the WAF. The WAF introduces 5 key themes or pillars. It's helpful to think of these lenses as lenses through which you consider your solution. The reliability pillar is about how our system remains available and recovers from failures. The performance efficiency pillar helps us to ensure our system is responsive even when we experience load. The security pillar helps us to consider how we mitigate threats and risks against our system and its data. The cost optimization pillar is about how to understand and reduce our solutions budget. And the operational excellence pillar relates to how we deploy, monitor, and manage our system in production. And we'll talk through these pillars in today's session and use them to identify some of the key requirements you need to consider for solutions in Azure.
Okay, Ripple. So those areas all make sense as things we need to think about, right? But sometimes I guess those different areas might not all apply, right? Or maybe we need to prioritize one thing over another. Is that fair to say?
That's right, again. As you can imagine, with all these different types of lenses and requirements, it'll be hard to figure out how to balance them all. And sometimes you can't have everything you want. So you might need to make trade-offs. For example, let's say you're considering 2 different solution architecture proposals, 2 options. You might think initially that one of them better supports your business requirements. But when you factor the technical considerations in, you discover the other alternative has some advantages. You also need to consider the relative cost of implementing and running the 2 solutions and the performance you're going to see from each of these alternatives. And you also need to consider security, right? So, how secure would your solution be? Um, and The next one, which happens, is reliability. Uh, when you factor in the reliability of the solution, things get more complex again. So it's basically important that you actually also look at the usability, which might tip the scale towards one direction again. And similarly, so might the way your support team can help customers when they have problems. And similarly, so might, sorry, I'm running a little behind on the slides. And overall, the solution complexity for one or the other also factors it in. So you might end up selecting one of these alternatives after considering all of the trade offs, weighing up the options, thinking through which one matters the most for your business. And for this particular case, as we talk today, we'll highlight some of the common trade offs that we need to make when we consider each area of the non functional requirements. So, John, can you start us off talking about how we think about reliability?
Absolutely. So, in my team, we work a lot with customers who are building highly reliable, highly available solutions on Azure. And one of the key things that we do when we talk about reliability is to distinguish between two different but related concepts. The first is availability. Availability is how our system works during normal day to day kind of operations. And this includes how it copes with things like small glitches. So things like network outages and other transient failures, things that aren't going to be long term, but that might just be little blips in our system. And then we distinguish this from recoverability. Recoverability is more about how our system works during a disaster or even something like a planned failover. And although both of these two concepts relate to reliability, we consider them differently and we think about them being associated with different kinds of requirements. So let's talk first about availability. When we think about what our availability requirements are, we need to ask ourselves a set of questions in three areas: the business context, dependencies between the system we're building and others, and the consequences of unavailability. So first, let's try and understand the business context. Now, it's really important that we understand the business criticality of the system. How critical is it to the business? This might seem obvious, but it's really crucial.
That's a good point. Once I worked with some technical stakeholders who told me that the system needed to be rock solid and bulletproof, regardless of the cost. But later, when I spoke to them, some of the business owners of the system, they made it very clear that if the system wasn't available for a short period, it didn't really matter to them. This requirement didn't get translated properly to the technical stakeholders.
Exactly right, Ripple. Not all systems are critical to the business, to the organization. So, for example, an internal system that employees use to submit requests for training courses, say, that's very, very different to one that your customers use to place orders. So, by having a realistic view of the business criticality of your system, you can start to make some decisions around how you prioritize systems and also what's worth investing in and how to invest appropriately in different parts. And you also might identify specific requirements that you need to follow because your industry requires them or because of compliance standards that you need to meet. Now, a related but different question is how frequently the system is used. It's possible to have systems that are business critical, but that are only used occasionally. So, for example, a month-end accounting processing system, right? Or a system that you use to submit tax returns. You don't use these every day, but when you use them, they're really important. Likewise, you might have other systems that are frequently used, but that aren't critical, right?
Mm-hmm.
Cool. So next, let's consider the dependencies between systems. Does anybody else depend on the system you're talking about being available? If they do, and if they themselves are a business critical system, that means that you probably inherit that business criticality as well, right? They can't do their work if you're unavailable. And equally, you need to consider your dependencies too, the systems that you depend on. So if you're depending on a system that's unreliable, are you going to have a problem with your own availability too? Now, there are strategies that you can often use to minimize the impact of downstream services being unavailable, but you need to understand that landscape to make an informed decision and a plan. Next, we need to consider what happens when the system is unavailable. Is it a complete disaster and your whole business shuts down, or is it just an inconvenience? So, for example, could you fall back to manual processing? And if you can fall back to manual processing, how long can your team sustain doing manual processing before they become overwhelmed or before it starts causing problems? It's also helpful to think about your users as well. So if your system is unavailable, will your users notice? In some cases, they might not even notice if it's something that only they're going to use very intermittently. If they do notice, at what point are they likely to start complaining about it, right? And if you've got a back-end processing system that's several steps removed from your users, maybe they won't notice things like short gaps in connectivity or availability at all. But for your public-facing website, they possibly will.
John, I've heard the terms SLA and SLO used to talk about some of these kinds of things. Are they the same thing you're talking about here?
Yeah, kind of. These terms are pretty important because SLAs and SLOs both refer to requirements that we're committing to. Now, the two terms, SLA and SLO, they sound very similar, and sometimes people use them interchangeably, but they really are quite different. A service level agreement, or an SLA, is a commitment we've made. So maybe we've got a contract with our customers, and if we have to give them a partial refund, for example, if we don't meet an agreed level of service. On the other hand, a service level objective, or an SLO, is our target or something that we aim for, but there aren't necessarily any immediate consequences for failing to meet that target. Now, the way that we typically represent our availability requirements is through a percentage of uptime. And normally we measure that by convention over the course of a whole month. So let's say if we need 99.9% uptime, which is fairly standard for many systems, then that means that we're allowing for about 43 minutes of downtime per month. And sometimes we call 99.9% 3 nines, right? 999, 3 nines. Now, of course, having 3 nines doesn't mean that your system is guaranteed to go down for 43 minutes a month, right? But what it does mean is if the system does go down and it goes down for 43 minutes or less a month, it's not unexpected.
So sometimes people might say my system is critical during the business day, but not so critical at night or on the weekends. How do we handle these kinds of requirements?
Yeah, it's important to remember that we can't choose when downtime happens, unfortunately, because problems and outages don't happen on a schedule. If they did, that would be convenient, but then we could fix them in other ways, right? So saying things like we need 100% availability during business hours doesn't really work, unfortunately. You need to think about this as the entire month. Now, what you can see is that as you raise or lower your availability percentage, the allowable downtime for your system changes significantly. And so the differences between the percentages, if you just look at the percentages themselves, they might seem fairly small, right? 99.9 to 99.95 to 99.99 doesn't seem like a huge difference. But as you can see on the slide, it really does make a big difference to the actual real number of minutes that you're allowed for downtime per month. So we have a website, uptime.is. It's not a Microsoft website, it's a community website, which we use a lot to figure out what an availability percentage translates to in real terms. And it's a really useful resource. Now, one technique that some organizations use to plan their availability is to plan for application tiers. So for example, you might have gold and silver and bronze tier applications. Each of those have different availability requirements. And then they also might have different levels, for example, of monitoring to support that, and maybe different kind of support policies as well. So by tiering applications and by using tiers, you can reduce the complexity of managing lots of different solutions or workloads in your company that might have different requirements, right? You make them more standardized. So when we think about having a real world solution, right? A real world solution has multiple components, and we need to very carefully consider which parts of the solution need to be operational for our whole solution to work correctly. So let's take an example. Let's say that we have a solution with a web application, an application that talks to another application on a virtual machine, an Azure storage account, and say a database as well. So it's important to be aware that any of these components might fail, and they also might fail at different times. So when we consider the overall availability of our solution, we have to account for independent failures of different components at different times. Azure provides an availability SLA for each of our services, and it's important to read these SLAs very carefully to understand what they mean, and also to understand how you need to configure and use the service to get the benefit of those SLAs. That's a really important thing when you're architecting a solution, is to actually read those SLAs carefully. When your solution composes multiple Azure solutions together, Azure services together, and depends on each of those services, then you effectively multiply all of those availability percentages together to work out what your solution's composite SLA is. So in this case, the solution has a composite SLA of 99.69%, which translates, according to uptime.is, to about 2 hours of allowable downtime every month. Now, composite SLAs aren't a perfect measure, and they don't indicate that you should expect that level of downtime, but they can be helpful in a couple of ways. Firstly, if you've committed to an SLA that's higher than what your solution's Azure composite SLA is, that indicates that you might need to revisit your requirements or your expectations, right? You're committing to something that you aren't necessarily going to be able to meet. And secondly, you can use composite SLAs as a tool to help you evaluate different possible architectures and to consider how you might apply different controls to minimize the risk of downtime.
John, it's not always easy to define what downtime actually means, is it?
No, that's a really good point. Defining what up and down means can actually be surprisingly difficult. So defining up tends to be pretty easy, right? If everything is working normally, then we'll say the application is up, right? That's fairly straightforward. And if a critical component like your database, for example, is unavailable, then you might say the whole application is down, right? Even though the rest of the solution is working, the database being down means nothing effectively works. But then things can get a bit more complicated. So for example, suppose that all of your systems are running, but everything is unusably slow. So would you say the system is up or down in that case? Or let's assume that you have health checks that run from lots of different places around the world. And suppose that because of, say, some networking issues, health checks from some locations are saying that everything is okay, but then checks from other locations are saying that something is unhealthy. So how do you decide what the actual health status is when you've got this kind of conflicting information? So there's no single answer to these questions, unfortunately. You need to decide for yourself what up and down mean to you and how you operationalize that for your solution. It's also important to consider that some parts of your solution might be more important than others as well.
So, for example, if I'm building the e-commerce system, which we talked about, then accepting and storing orders might be more important than fulfilling them immediately.
Yeah, that's a really good example. As long as the orders are received and stored, then you can always go back and process them later, right? It's not a disaster if they're not processed instantly. So when we calculate composite SLAs, typically we consider our hot paths, right? The paths for our application that have to be online. And this means that we might be able to actually raise our kind of real world overall composite SLA by designing our solution to fail gracefully and to still work well even when a component is unavailable. So in your example, Ripple, writing those transactions out to somewhere like a storage account or a database, and then being able to process them later kind of removes that dependency on some of those downstream components. And we might then focus on measuring and improving the reliability of some parts of the solution, and then choose not to worry too much about others. So we've talked about availability. Now let's talk about recoverability. So let's look at an example timeline of a scenario that happened during a hypothetical afternoon. So suppose that your system has some sort of catastrophic failure at, say, 2:30 p.m., 2:30 in the afternoon. Now, luckily, it happened during the business day and your team was working. And so they very quickly figured out what the problem was, and they were able to restore the system from a backup by 4 p.m. So in this scenario, the recovery time, the amount of time the system was offline, essentially, was 90 minutes. But the last database backup that was taken before the disaster struck was at 12:30 p.m. And so when your team restored the database, they effectively lost 3.5 hours of data, right? And this is what we call the recovery point. These two terms, recovery time and recovery point, are really important when we think about our system's recoverability. Recovery time is how long it took for us to restore the service to our users. The recovery point, on the other hand, is the amount of data that we lost in the process. So these two terms describe what happened in a disaster. We use them retrospectively when we're discussing what actually happened in a real disaster scenario. There's also a couple of other terms that you might hear as well. Mean time to recovery is how long, on average, it takes for us to recover from outages. Mean time between failures is how long, on average, we go between outages. So ideally, we want our mean time to recovery to get shorter and our mean time between failures to get longer. Now, normally we don't set these two numbers, the mean time to recovery, mean time between failures, as requirements, but some organizations use them as a way to think about the outages they've already had and to try to improve how they've handled them in the future. But let's go back to those basic terms, recovery time and recovery point. When we want to set requirements and when we want to anticipate how we'll recover from outages, we use the term recovery time objective and recovery point objective to describe those.
So they are objectives because they are what we are aiming to achieve or exceed?
Exactly, that's right. And sometimes we use the terms RTO and RPO for short. So these are our requirements, right? And if we say that we have an RTO of 10 minutes and an RPO of 1 hour, what that means is that in a disaster scenario, we could be down for up to 10 minutes, and we're accepting that we might lose up to 1 hour of data in the process. Now, let's suppose we're okay with the idea that in a disaster scenario, right, so not day to day, but in a disaster scenario, our system is going to be offline for a few minutes, but we want to try and reduce or even eliminate data loss. So let's think through an example scenario for this. Suppose that we're going to deploy our system to the Australia East region in Sydney. Now, one of the disasters that we might need to worry about is some sort of regional disaster that affects the entire Sydney region, that results maybe in some major loss of network communication for all of Sydney. These kinds of scenarios really aren't very likely, but let's say that our business stakeholders have decided they want to completely mitigate that risk, or at least they want to investigate it. So one option is to ensure that every single time we have a transaction going into our application, we replicate it to another region that's geographically separated. So for example, Australia Southeast, which is in Melbourne, in Australia. So let's take an example request to our application. Let's say that I, here in Auckland, New Zealand, am sending a request to our application. So first, the request needs to hit our application tier in Sydney. Then the data storage happens both in Sydney and also in Melbourne, and it's acknowledged from Melbourne back to Sydney. Only at that point will the client be told that the transaction is done. So we call this kind of process synchronous replication. And what this means is that if we experience a catastrophe in Sydney, then we know that Melbourne has a complete copy of our data, right? So from a recoverability point of view, it really helps us to resolve that requirement. But this comes at several costs. Firstly, we have to pay more for the extra resources in Melbourne, right? Plus, we also have to pay the cost of sending data across the network. And so these kinds of decisions make our solution architecture more complicated. Even more significantly, there's a performance impact because every transaction has to be copied across those two regions. And because of the geographic distance and because of the speed of light, there's an 18 millisecond latency between these two regions. Now, this might not seem like a lot, but most applications end up making multiple updates to a data store to process one business transaction. So 18 milliseconds can actually add up very quickly and be something that users really notice. So we might instead decide to asynchronously replicate our data. So what this means is that when a transaction arrives in Sydney, we complete it straight away and we acknowledge it back to the client straight away. Then sometime later, we send a copy of that transaction off to Melbourne for storage. So when we asynchronously replicate our data, it means that our performance is much better because we don't have to wait for those changes to be acknowledged in two different regions before we consider it to be written. That 18 millisecond latency still happens, of course, but it can happen at some point in the future. It doesn't slow down the transactions for our clients. But if we do this kind of approach, then our RPO, our recovery point objective, increases because the frequency at which we replicate the data affects how much data we might lose. So, for example, if we replicate data every 10 minutes between Sydney and Melbourne, then in a disaster, it's possible that we might lose up to 10 minutes of data. So our RPO for that kind of disaster is 10 minutes. But Azure also gives us another option too. In many regions, including in Australia East, we have multiple availability zones. So think of availability zones as being separate, independent sets of data centers, each of which have their own power, their own network connectivity, their own cooling, and so forth. Now, we put them in the same overall region. So, for example, in Australia East, all 3 availability zones are in the Sydney metropolitan area. And they're built to be far enough apart that they're unlikely to go down at the same time if something happens like a power outage, for example, in one area. But they're also close enough together that the latency between the zones is very low. And so what that means is that synchronous replication between zones is often actually quite feasible without a lot of latency. So if you deploy a solution using multiple availability zones, you increase the overall resilience of your solution because you're writing data across multiple physical sites while not really affecting your performance too much. But there is still a small risk that the entire region could become unavailable because of a large natural disaster. Honestly, that kind of thing is fairly unlikely, but it is a risk that some customers need to mitigate. And the good thing is, by providing zones and regions, we're giving you many different options for how you architect your solution and how to make trade-offs between performance and resiliency. So on the one hand, you could deploy a single zone solution, which gives you very high levels of performance, but without a lot of resiliency. You could deploy a multi-region solution, which can give you much higher levels of resiliency, but with lower performance and potentially some higher costs. Or you can deploy a multi-zone solution, which can give you much better performance, also quite a lot of resiliency, and without as much cost. And typically, for many solutions, a multi-zone approach is now kind of what we're starting to recommend because it gives a good balance of all of these trade-offs. But your own business and you as an architect need to make an informed decision based on your own risk tolerance and based on all the factors involved in this trade-off. And this is only one of the many trade-offs we have to consider when we architect a solution, as Rupal was saying before. Does this specific trade-off, reliability versus performance, does this matter for your scenario? Well, it really depends. In some cases, no, it doesn't. In other cases, it matters a lot. So when you're thinking about your solution's reliability, availability, recoverability, it's important to keep all of these trade-offs in mind. If you make your solution more reliable, it's going to have consequences. It might cost more for the resources. It'll cost more to develop. Also, more reliable solutions can sometimes make your solution more complex. And as we just discussed, reliability and performance can sometimes be at odds as well. Now, speaking of performance, Rupal, can you tell us about the second pillar in the well-architected framework, please?
Sure can. We want our applications to perform well and to be responsive when users are working with them. We also want the data to be up to date. So when we design systems, it's a good idea to think about performance requirements. So we want what we want is one of the first things we need to work out is what exactly we are trying to improve. If you aren't clear on what the goal is, then you aren't going to be able to do much to meet it. Let's look at an example. Suppose you're building a solution that processes and pays invoices from suppliers automatically. An invoice arrives and is imported into a database. Then, ever so often, a processor component wakes up to process all of the unprocessed invoices, and it compares the invoice against the company policies, like the maximum amounts that can be approved for certain type of expenses. Next, it sends it to a human approver to review. And finally, once it's approved, the system's payment engine contacts a bank to arrange the transfer. Now, suppose we have been given the task of improving the performance of the system. The first question we should try to ask, which part or parts are we trying to improve? Correct? Because only then we'll be able to help them. If the goal is to improve the performance of the whole system, then we need to look at it holistically. There are multiple parts of this processing flow that might slow down processing, but have nothing to do with the code we write or anything we deploy.
So, for example, in this case, the whole process hinges on this human approver, right? So, what happens if they go on vacation, or if they just take a really long time to approve the expense?
Exactly right. Also, the bank's API is probably beyond our control. So, it's if that's the bottleneck, what do you do, right? So, it can be helpful to break the system down into individual components. For example, after thinking through where the pain points are, it might turn out that you just need to improve the speed at which invoices are imported into the system. This is a more manageable metric to optimize. But if we prematurely try to optimize one piece of the system without understanding the whole workflow, we might find we are spending our resources fixing the wrong problem. And there might be another component that's far more significant. This means that when we say we have performance requirements, it's important to be clear about exactly what's in scope for each requirement. But this is just one of the elements we need to think about. We also need to consider the strength of our performance requirements. We might have we might have a hard requirement, which means that we absolutely must meet the requirement or bad consequences might happen.
So, for example, going back to the e commerce example we used before, if we said we had a hard requirement that adding an item to a user's shopping cart must happen within 2 seconds, otherwise, we know from experience that customers are going to drop off.
That's right. But we might also have a soft requirement, which we try to meet but aren't necessarily going to stop us from delivering value to our organization. So, in your example, Joan, you might say that we have a soft requirement to add items to our shopping cart within half a second because this gives a positive customer experience and makes our online ordering system feel snappy. And you might even have hard and soft requirements in the same metrics. Next, we need to think carefully about how we measure and track how well we are meeting our requirements. Modern analytics software is really good at keeping track of how much time the parts of each transaction takes. We need to figure out how we take these raw data points and aggregate them to get an overall view of our performance. In some scenarios, you may want to look at the ranges, like the minimum and the maximum amount it takes for a particular transaction to happen. This may be good when you try to ensure that every user has a good experience. But in other scenarios, you want to look at percentages or averages as a way to determine a single number that you can target.
So, like in my example before, I said I want the average processing time to be under 2 seconds, right? So I'm saying average specifically there.
That's right. The average is a very simple metric to calculate, but it covers over the outliers, right? A very high and a very low value, right?
Mm,
Like or very slow or very fast transaction.
right.
Commonly, performance requirements are expressed as percentiles. For example, you might say that 95th percentile, you want items to be added to a cart within 2 seconds. What does this mean? This means that 95% of your transactions should happen at this speed, but 5% can take longer. Each of these ways of aggregating and summarizing your data makes a difference and are good for different scenarios. When you write the performance requirements, thinking about the way you will aggregate helps to ensure you're focused on the right things. And the next thing you need to consider is the actual target number. Should you say that you want items to be added to a shopping cart within 1 second or 2 seconds, half a second? How do we even know? Not every system needs ultra high performance. So, how do you know what your requirements should be, what that number should be?
Now, I'm guessing there isn't a magic formula that I can use to figure out what performance target should be for my solution, right?
Sadly, not. But there are a few questions you can ask to help that might help to come up with a number. First, it's helpful to consider the business context of the system or for the piece of the system you're trying to optimize. It's important to know how critical the system is to your business. Is it something that drives your ability to generate revenue? Or is it an internal training system that's only used by your employees? Also consider how frequently the system is used. Is it used full day, every day, by some of your users? Or maybe it's only used at the end of the month? And try to get a good understanding of the usage patterns. Some systems have peaks of usage at different times of the day or week. Others are only used inside or outside of the business hours. Understanding these factors will help to plan how you scale your system, and it also affects cost efficiency, which we'll discuss soon. And it's helpful to know how many users or transactions the system needs to process.
Because as you mentioned right at the start, right, it's very different to design a system for 10 concurrent users than for tens of thousands of concurrent users, right?
Yes, exactly. So, second, there are some questions about the technical context that can help you to plan your targets. You might already have baseline performance expectations from other systems. Maybe this is replacing an older system and you can record some metrics before you decommission it. So you know what you need to meet or exceed. What do the users expect? Or maybe there's a similar system elsewhere in the business that you can look at to get some ideas from. So, as we spoke earlier, understanding the wider context is important too. If you're focused on one component, understand what you depend on and who depends on you. If another system depends on you and has a strict performance target, then maybe that means you will inherit the same target. Equally, if you depend on a system that's known to be super slow or unreliable, then think about how you can ring fence that part of your processing so your performance can remain high even when the other system is having a bad day. A third category of things you need to think about is around what happens if you miss the mark and you perform poorly. In some systems, bad performance means you fail to meet your business goals. If you're building a point of sale system for a retail company, then a slow response time might mean that the queues build up in retail stores and people will leave, which costs the business sales. In other scenarios, there's no direct tangible effect of a bad performance, but over time, it contributes to a negative perception. And just like everything else we have discussed, we need to weigh up our performance requirements against our other requirements. Highly performant systems can cost more to build and run. You might need to spend more on higher tiers of Azure services to get more resources like CPU, memory for your solution. And even aside from the resource cost, it can cost more to develop and optimize a system for performance. Your developers might need to take benchmarks to use more efficient algorithms and approaches, or even to rewrite some core parts of the system. And the techniques you use to optimize your performance often make your solution more complex, which in turn means it might be harder to maintain in the future. So, this is performance. Next, John, can you talk about security?
Yeah, sure. Now, security is a huge area, and we're not going to get into it in detail today. We have lots of other Learn Live sessions, Fast Track for Azure Live sessions, and plenty of other content that cover all different aspects of security in a lot more depth. But what we're going to focus on today is security requirements, and specifically how we might determine what our security requirements actually are. When I talk to customers about security requirements, one of the very first questions that I ask them is, what are your obligations? So, for example, if you have legal or compliance or contractual requirements, usually we need to prioritize those ahead of everything else. And in certain regulated industries, there are particular rules that you might need to comply with, whether you want to or not. Increasingly, companies are also purchasing cyber insurance, and cyber insurance policies are starting to also require that you do certain things as well. But with all of these kinds of obligations, it's very important not to assume or to infer anything. Make sure that you get advice to understand exactly what the requirements really are. The exact wording of requirements can make a big difference to how you meet those requirements. We'll talk more about that in a moment. A second important consideration is who your security stakeholders actually are. In large organizations, for example, you might have dedicated security and compliance teams. Now, it's always a good idea to bring them in as early as you can because they'll be able to help you to understand what you're planning to build, and they'll also be able to tell you what they need from you at each stage of delivery as well. And last, but definitely not least, you need to consider the threats that you and your system are subject to. It's difficult to protect yourself against a threat if you don't actually understand what it is. And if you're just guessing about the threats that you might face, then it's easy to protect yourself against the wrong things and leave yourself vulnerable to actual threats. So let's talk about a few things to consider when you think about threats in the context of your security requirements. First, make sure that you don't confuse requirements for security controls. Security requirements are often based on threats. Security controls are the actions that you can take to mitigate that threat or to meet that requirement.
So, to think of an example, would a requirement be something like protect my web application from denial of service attacks?
Yeah, that's a really good example of a requirement. Yeah.
And then there might be many different security controls that I can apply to achieve that requirement.
Exactly. And depending on your solution architecture, that might include using something like Azure DDoS protection. It might include using something like Azure Front Door, right? There's lots of different ways that you could potentially achieve that, which you don't really understand if you zoom straight on the control. So once you understand the requirement, then you can make a list of all of those possible controls that can mitigate the threat. And then you can decide which controls to apply based on an analysis of the trade-offs involved in those controls, because some controls have far more serious trade-offs than others do. If you come in saying right from the start that you need to use a specific control, you're not actually working with requirements, right? You're also making your life harder, because there may well be better ways to achieve the requirement that don't require that control and therefore the trade-offs that it brings. And when you think this way, you can also look outside of the box a little bit as well. So, for example, some organizations, as I mentioned, are now looking into cyber insurance, and that sits alongside other controls that you can apply. Cyber insurance can help you to mitigate the costs of a cyber attack or a data breach or something similar. Now, next, when you think about the security of your solution, you need to look beyond just the code you write yourself or the Azure resources that you deploy directly. So, for example, the way that your team handles things like source control and code review can make a really big difference to your security posture. If you have important code reviewed by multiple people, it makes it less likely that there'll be bugs or issues. And modern software is built on top of open source modules and libraries and a whole ecosystem of products. So what happens if one of those products introduces a security bug? And this actually happens quite a lot. You might have heard about vulnerabilities in the last year or two in products like Log4j, for example, and in libraries distributed through Node Package Manager, NPM. So your organization should have processes to review and harden your use of these kinds of tools. And it's also critically important to consider your Azure governance strategy. Carefully consider who you grant access to your environment, what kind of access they have, and what scope they have it at. Because otherwise, any other controls that you put in place could just be removed, right? If somebody can come in and modify the permissions, for example. I also want to call out a couple of specific areas of security that often come up in requirements discussions. Firstly, try not to focus on network security as the primary way that you secure your solution. In on-premises solutions, we typically use the network as a boundary to prevent unauthorized people from using our system. But in the cloud, the main security paradigm that we think about is identity. So that's either a user's identity or an application's identity. And principles like zero trust networking help us to consider how we can secure a solution even when it's reachable, for example, across the public internet. It's also important to remember that cloud environments aren't the same as on-premises environments, so our requirements shouldn't treat them as if they are. And even more importantly, our controls shouldn't treat them as if they are. Now, there's a lot more detail on this in other sessions, including some of the networking sessions, both in FTA Live and Learn Live as well. Now, as I mentioned, identity is a key part of how we secure modern applications and modern solutions. And in any system that we design, we need to think very carefully about all of the different identities that might interact with us. This is true for internally facing applications that's going to be just used in our organization, as well as anything that's going to be exposed to our customers. So make sure that you think about identity as one of the key parts of your requirements when you're considering your security posture. Now, security has a reputation for increasing the complexity of a solution. And frankly, often the increase is actually justified. And similarly, the cost of building and running a solution might also be higher than building a non-secure solution. Again, I think that's probably also often worthwhile.
I think next we move to operational excellence, which is the fourth pillar, which is what we call operational excellence. In the Azure Well-Architected Framework, operational excellence includes a range of different scenarios. I think we lost John, uh, and we might need to wait for him to come back. But we can talk about the trade offs which John was talking about while he comes back. Like overall, it's true that security can increase the complexity of your solution, and often that increases in complexity is justified. Similarly, the overall cost of building and running a secure solution might be higher than a non secure solution, and this might also be worthwhile. And if we don't have a clear understanding of the security threats and other requirements, we might end up increasing complexity for no good reason. So, just wrapping up what John was talking about before he comes online. So, John,
Hello,
welcome
sorry
back.
about that.
No,
Thank
no
you.
worries. I did
I'm
complete
not
the
sure what
security one.
happened there.
Yeah, I just did
Excellent.
complete
Thank
the
you very much,
security
Ripple.
one, but we are ready to
Great.
move on to the operational excellence part of it. If you can share that.
Yes, great. Sorry, I'll just sort myself out. Some slight technical issues here. There we go. Hopefully those slides will come through any second. Right, we're back in business. Okay, so let's move on. That was a good point to take a little break. Let's move on to the fourth pillar in the well-architected framework, which is what we call operational excellence. So in the Azure Well-Architected Framework, operational excellence includes a range of different concerns. But here I want to focus on one that we've already mentioned quite a few times in today's discussion. And that is, don't underestimate the importance of considering solution complexity. If your solution is so complex that nobody can understand it, then they won't be able to do things like make improvements or make bug fixes. You also need to think about what your team can realistically manage. If your team is already smashed with work, then giving them a whole new technology stack to learn or a complex business domain to build for isn't likely to go very well, right? And think about the size of your team. If you've got a small team and they're already very busy, will they have bandwidth to pick up a really complex solution? What's the skill set of the team? Are you asking them to implement something that they've never done before? And an underappreciated concern as well, especially in larger organizations, is the longevity of your team. So if you tend to disband teams frequently, so for example, after delivering a project, then you need to make sure that your solution is understandable to whoever's going to pick it up next, whether that's another team or an operations team and so forth. And when you consider solution complexity, consider it as part of the total cost of ownership of your solution. So for example, in Azure, you can choose to use infrastructure as a service, platform as a service, serverless, all these different kinds of Azure resources. With IaaS, infrastructure as a service, you take on more operational burden. So for example, you have to handle virtual machine updates. With PaaS and especially serverless, you make a lot of that, those operating system updates, for example, Azure's problem, right? We take care of that for you. But you are still responsible for keeping up with platform updates. So for example, in app service, you need to make sure that you're keeping up to date with any changes that we make to the app service platform. And total cost of ownership includes those kinds of ongoing updates. Modern software isn't just built once and then forgotten about and left to sit on its own. It needs ongoing attention for things like security patches, bug fixes, platform updates, and of course, new features and capabilities as well. Now, when we think about building and operating our system, we usually talk about DevOps, and you might have heard about DevOps before, right? But importantly, DevOps isn't just about deployment. It often gets considered in the context of deployment, but really it's about how people and processes and tools all work together. Now, once again, we aren't going to get into detail on this here, but there have been some other Learn Live sessions around modern service operations and DevOps that provide a lot more detail on this as well. And when you're thinking about your operations requirements, think about things like how your code will be developed and reviewed, how it will be deployed, how configuration changes will be applied as well. Increasingly, automation is becoming a critical part of deployment, management, and so forth, especially for cloud resources. Automation reduces the likelihood of accidental mistakes and inconsistencies. And as your solution grows, it saves your team time and helps to ensure that they're focusing their attention on the most valuable things that they can do. So think about whether and how you can automate your operations as well. And you need to think about monitoring and improving your system. Throughout today's session, we've spoken about all sorts of different requirements across the 5 pillars. And many of these can be monitored and reviewed. So think about how you will actually do that so that you know whether you're meeting all of those requirements we've spoken about. And think about using the WAF while you operate your solution, right? The well-architected framework isn't just a one-time thing. Review the metrics across all of those 5 pillars and use them as lenses to review how your production system is going. Maybe do that once a month or once a quarter. See how the solution is performing against your business requirements and where you might need to make tweaks. And also remember that architecture isn't something that you typically just do once and then it's set in stone and you can't change it. Instead, you need to keep reviewing your architecture regularly as well. And it's common to change your architecture significantly as you grow or as your requirements change. Now, as always, we need to think about our trade-offs across each of these requirements. And when it comes to operational excellence, there are 2 common trade-offs that often emerge. The first is how agile we can be, while also adding processes that minimize risks and mistakes. Different organizations and different industries often end up adopting different ways of building software based on things like risk tolerance, organizational culture, competitive pressures, and also their track record as well. And again, automation is a really key part here because it allows you to remain agile and remain very fast moving while minimizing risks and mistakes by ensuring that humans are removed from the pieces that they don't need to be involved in. And then a second trade-off is around the level of complexity that you're prepared to accept in your solution. As we've seen throughout the discussion, sometimes complexity is necessary because you need it in order to achieve higher resiliency, higher performance, higher security, whatever. But complexity has negative effects too. A more complex system is more error-prone. And as we spoke about, it's also makes it harder for you to make changes and improvements in the future. So Ripple, how about we now move on to the final pillar in the well-architected framework?
Sure. The final pillar of the well-architected framework is cost optimization, which helps us understand the amount that our solution costs. Overall, one important consideration to keep in mind is whether your solution is a profit center or a cost center. Profit centers generate revenue. So, example, if you're building an e-commerce system, it probably is a profit center. Cost centers generate revenue, don't generate revenue. So it's often very important to keep their costs down. So your cost optimization requirements might be very different depending on which type of solution you're building. It's also critical that you have an understanding of your solution's budget, both to develop and to operate.
Yeah, it's always interesting to me, Ripple, when I speak to customers and ask what they plan to spend on the solution that they're deploying and how much would be too much for them. And they just have absolutely no idea, right?
Yeah, that's true. And if you don't have a specific figure, try to at least think about a range or a maximum which you would like to spend. So by having a budget, you can ensure that you consider cost as one of the trade-offs across each of the other decisions you need to make. And you can even set a budget on your Azure subscriptions to ensure you're alerted if your charges start to increase. Increasingly, organizations are also starting to think through sustainability requirements and commitments. For example, you might have targets for the level of emissions your solution can generate. The good thing is, designing a sustainable solution basically just means you're also designing a performant and cost efficient system too. So it's often a win win. And finally, it's important that you project out the solution cost. So make sure you project out the cost of your Azure resources and factor in elements like networking bandwidth, you might also be able to offset some of your costs with hybrid licensing benefits. Don't just focus on the Azure or technology costs, though. John and I have spoken extensively today about trade offs around solution complexity, processes, and how that can affect your staff costs. For some solutions, you might bring in a consultant or a managed provider to help you build or operate it. This should all be factored in into your projected costs. If you determine that your cost exceeds your budget, or you just want to look at how to reduce your solutions cost, there are a few things you can think about during your requirement stage that will help to set you up. For example, think about the usage patterns of your solution. Are they unpredictable and spiky? Then maybe instead of provisioning a ton of capacity for your solution components, think about whether you can use elastic scaling approaches with the Azure services that you're using. Or if you have predictable usage patterns, then consider having the platform automatically scale up or scale down around your peak times. And think about things that you can do to reduce the cost of the resources themselves. We already spoke about hybrid benefits, which can reduce the cost of your Azure resources when you have previously purchased the licenses for some of the Microsoft products. Another example is Azure reservations. If you commit to a term like 1, 2, or 3 years, then you might get reduced rates on the resources for that time. And for the non production workloads, you can look into using dev test pricing, which can reduce the cost significantly. Just some of the levers you might want to try out. And finally, we need to think about how we are trading off our cost and budget against other parts of the solution design and requirements. One way you might reduce your cost is to deploy cheaper, less powerful types of resources. This might reduce your cost, but as John mentioned earlier, it will also reduce your performance. And in some situations, it might reduce your reliability too, because some resources types provide better resiliency at the higher tiers of the resources. You can also sometimes save money on Azure resources by building more complex architectures, such as using infrastructure services like virtual machines instead of platform or serverless services. But be careful here of false economies. When you factor in your staffing costs and all of the other aspects, the total cost of the solution is often higher if you focus solely on reducing just your Azure resource costs.
Awesome. So, as we start to wrap up, I should mention that today we really only scratched the surface on these different areas, right? Each of these requirements that we've discussed, each of the well-architected framework pillars, has a lot more that we could say on each. But today, what we've tried to do is talk through the big areas that you should think through in each of these topics. Our goal has really been to introduce you to the key concepts and the types of requirements that you typically need for most solutions. We've also tried to set you up to have further discussions with your solution's technical and business stakeholders. And what we really wanted to highlight repeatedly is architecture is a process of making trade-offs. To be able to make the right trade-offs for your solution, you need to understand your business requirements and your goals really well. And doing a formal architectural review can help you to think about these requirements and trade-offs in more detail as well. As Rupal mentioned when we started, we've got a number of links for you to take away, and I believe Satish has been putting some of those in the chat too as we go. One of the links is a document summarizing the key requirements that you typically need to consider and linking to some of the helpful resources that we've discussed today. And of course, we've also linked to the Azure Well-Architected Framework, which helps you to think through these questions for your own solution and provides a lot of different insight into how you can configure your Azure solution to meet best practices and to meet different kinds of requirements across these pillars. Now, this, of course, is one in a series of episodes of Learn Live, so please don't miss the next one, which will be on Azure Machine Learning Developer Experience. That's just in a couple of days' time. But with that, all that's left to do today is to thank Rupal and the rest of the team here at Learn Live for today. And of course, thank you for joining Rupal and me today and wish you the best of the rest of your day. Thank you.
Thank you.